So let's do question 1. So basically you have to graph the Maxwell-Boltzmann speed distribution for these 3 gases at 273. It says to put them all on one graph, but you can start out by having just one of them. You might want to pick helium to start with. And this is very important. And I'm going to show you how to basically do this here. You always do a full calculation of there's 2 popular equations for Maxwell-Boltzmann distribution. Do one by hand on paper, and this one says 100, but I think the one I'm going to choose is 1,000. I'll show you the answer that you get, and that's how you make sure that your Excel, the way you typed in the calculation in Excel, that's how you make sure that it is correct. So the one thing I wanted to show you first was when you graph all 3 on one page, you'll see that helium is this one, has a very broad distribution of speeds, right? This is nitrogen, and then the most heavy one, which is iodine, has a very narrow and thin distribution of speeds. And you'll notice that this one actually has a number. So technically, what I have right here is not exactly what you're going to graph. It's very, very close. The only difference will be the number, and I'll show you. So when I started out, I purposely chose 10,000 particles, just as an example. So if you look here, this says number per unit speed. So if I chose 10,000, units is 1 over, or the number over, meter per second squared. So iodine, if you look at here, that's 60. And it looks like if I was to say this speed was 140, the number of particles in my sample of 10,000, it looks like 64 of them. When you graph yours with the formula, if you do it properly, you'll have the fraction, and the fraction is what is the number out of 1, right? So notice if I happen to choose 10,000, right? The number of iodine particles out of the 10,000 that are at 140 meters per second, roughly 64 of them. When you graph this exact same thing, you'll divide this by 10,000. So you're going to have 1, 2. So you're going to have 1, 2, 3, 4. So 1, if I could see it, 1, 2, 3, 4. 0. Yeah, 0.0064 is what you'll get. So it'll end up looking like, it's going to look pretty much the same. I am going to hide the Excel formula. Your graph is going to look like this. Exact same shape, and I truncated it a bit because helium goes off, but you'll see how now it's just a fraction. So look at the numbers, right? So that iodine one is 0.0064, just like I said. So yours will look just like this. So don't be afraid of these weird looking numbers that get really small. So the first thing that you should probably do is just let's look at, and I have it written here, so I'll take you through it. So this is one way of writing the formula. This is the one that I happen to use, and it has the mass of one particle, right, in kilograms, and K is Boltzmann's constant, 1.38 times 10 to the minus 23 joules per K. And there's a few things that we know. We know that R, the universal gas constant, is equal to Boltzmann's constant times Avogadro's, so I could rearrange this for K here if I wanted. We also know that the mass, so if I know the mass, for example, of one carbon atom, and if it was in grams, just for instance, if I multiply it by Avogadro's number, which is in units of per mole, I know the mass of one carbon atom, it would be times 10 to the negative 24 or something like that. If I multiply it by this, you will get the molar mass. So molar mass is equal to Avogadro's number times regular mass of 1. We know that we've also seen this before, which is a different formula. So a lot of people get this confused with this. It's related, obviously. These are 2 different ways of calculating capital M. Okay? This is the one here that we're interested for today, because the second formula that you're going to see most often used is capital M for molar mass over R. The formula up top was little m and it had K, just like up here, right? So we can show real quick if we're doing a derivation of sorts, right? So if I start off with a formula up here, that was m, little m over K. I can replace K with R over N in the denominator, and then invert and multiply, and realize that m times Na is capital M. So I can replace m, little m over K with capital M over R, and this is the formula that we can use. But just be aware, if you choose this formula, which is the one in your textbook, I recall, that capital M has to be in units of kilograms, and you'll see that with the unit analysis why that has to be. So that is one quick look at units. Next up, we have, this is a closer look at the unit analysis, and I happen to use little m over K, but the same thing will work out. So what I've done is I've replaced, I didn't put numbers in, but I put the units for each of these symbols in here. So anything that has a unit, I put it in. So you can see that mass is kilograms, K is joules per K, temperature is in K. This is to the 3/2 exponent. Next up is V squared, so mass over mass, meters per second squared. E, right? All of this gobbledygook in the exponent has to cancel all of its units out, because E to a number with units is no good. So this proves that the units will cancel out. You'll have none left on that one. So what's left over is this piece and this one. So that I brought down here. This, what's left over, I put in here. And you'll see what I did right here. Shows what cancels. You're left with this. And what I chose to do, the 3/2, that exponent, I split this exponent into sort of two right here. You can pull the 3 out and then put in inner brackets the 1/2. And the reason is meters squared per second squared. When you take the 1/2 of this, obviously it's a square root. So it's kind of convenient. You're left with now, when you apply the 1/2 to this, the square root gives you meter per second. Now you're going to cube it. So meters cubed, seconds cubed, and it's 1 over this. These 3 will cancel out these 2. You're left with 1 over meter per second squared. And this makes sense, because this is taking you through, if you were to graph the fraction of your sample of particles, the fraction out of 1, that have these speeds. So let's say that you just happen to take a look at speeds of 35 to 40, that range. And let's say we're going to approximate the area under the curve with a little rectangle. We'll approximate it. So that rectangle kind of looks like that. So what are the units? If somebody said the fraction out of the total in the range will be the area under the curve in that range. So so if you're doing length times width, the y-axis direction of your little rectangle is 1 over meter per second, and the width of it is meter per second. So you multiply it out, you get no units, as it should be, because this represents, in this example, the answer to the question. What fraction out of the total of my sample have a speed between 35 and 40? This area will give you a number that represents the fraction out of 1 that have speeds in this range. So that's what it means. So we're good with that. Next up, we have the all-important calculation you must do by hand. And that's what this is meant to show. Plus, we do the units sort of again. So I chose this formula. You can use capital M over R here and here, right? That's the one your textbook has. You get the exact same answers. But what you want to check is this. Choose helium, right? The temperature, 273, and then the speed. I chose 1,000. I know that your assignment says choose 100. I mean, you can. I just happen to have the answer for the 1,000. So put in that for your velocity, this for your temperature, and this, when you get it in my formula, m in kilograms. and start multiplying it and calculating it by hand. So you see how long it took to make sure you're careful, and this is the answer that I get for helium, 1,000 meters a second. This is the number that when you make Excel start calculating for you, make sure that this is the answer you get. That's how you know your Excel formula you typed in was correct. Now, if you have trouble with that, I can try and help you with it. The Excel, the use of brackets and symbols, you got to be very careful, especially when you try and type it all into one cell. So be careful with that. If I'm not mistaken, you might end up, and I'll just show you real quick. This is my Excel, super small, I can't really see it, but you can see how I chose to type it out the way I wanted. This is my final answer for the fraction, right? That's going to be my y-axis. And this right here is the speeds. I start at 0 and I put in numbers. I populate it with as many as I need to get the shape on the graph, and that was helium. So then all I did was go over here and have the same thing happen for nitrogen, and then the same thing happen for iodine. So you populate as many values of velocity as you need to, clear as day, get data points. So what you're going to find is this. If you were to graph helium first, see how I got spacings here? These were tighter. You're not asking Excel to put an actual graph line on this because it won't fit it very well. So what you're going to do is make sure you put in enough data points so that you can see with your own eyeballs the shape of the graph. So iodine and nitrogen, you really have to populate its peak area with more so that you get the shape up there, right? If you picked a point here and here, these 2 points is all you would see. So for iodine, it was critical to add in extra points as needed to see the curvature, right? And I think if you're looking at this, you should already know from this what speed ranges you really need a lot of points for iodine. For nitrogen, it's this range, but for helium, you got to go all the way out close to 2,500 to get its shape showing. So that's it for question 1. So question 1, I guess, is not exactly done. I'll retract that statement. How does the most probable velocities compare? So you need a formula for that. Most probable, you look up in your notes, and the velocity of the most probable, there's a couple of versions for it, but one of them looks just like that, right? So what you'll do is you'll get one, you know, for iodine, you'll get one for nitrogen, and then you'll get one for helium. You just change the molar mass for each of them. Make sure your units work out, but you'll get numbers for these. And the most probable is supposed to calculationally match what you can pretty much see by eye. So the most probable is the peak of each of these curves, right? And iodine's most probably there. So you can look on your graph to see how it compares when you calculate using the formula. So that would finish question 1.